this is a first for this room. So it's such a distinguished pleasure to introduce our speaker today, Professor Conway. I think he's a national treasure, and I don't think we need to introduce him. So I try to say a few words that are just for maybe the people here that are new, maybe the students. So John was born in Liverpool, England, and actually his father taught chemistry the Beatles, two of them. And I would guess that John Lennon would be one of them.
I have forgotten which pair they were. I can find out, but by the way, later the Beatles bought the school.
Very interesting. We want to hear some more about this during the talk. So there are too many awards that Professor Conway received. I'm going just to say Fellow of the Royal Society, Pólya Prize, Nemmers Prize, Berwick Prize, many others. He worked in many areas of mathematics and physics, combinatorial game theory, geometry, geometric topology, group theory, number theory, algebra, algorithmics, and theoretical physics. And he is the John von Neumann Professor of Mathematics and Physics. And John von Neumann is
not of physics, no.
Of mathematics. Not of physics.
No, but I'm distinguished. You can say that.
All right, that
the John von Neumann Distinguished Professor.
John von Neumann Distinguished Professor of Mathematics at Princeton.
You're an extinguished professor.
well, on this visiting card thing, it says Dist Professor. And so my friends, or my enemies, whoever they are, say, what does it mean? Disturbed? Distracted? Distraught? You know.
So as John von Neumann, Distinguished Professor of Mathematics, I think if I would like to name one mathematician that is in the same mathematical
no, don't do that.
Type of mathematical research like John von Neumann, I don't think I can have another name other than John. He worked in so many areas, making so many fundamental contributions. And so I thought about a number, because John likes numbers. So I said, what number could be associated with John? So John von Neumann in the 50s said that mathematics is too broad now for one person to know all of it. No more than 1/4 can be known by a person. He was referring, of course, to him. My guess is that John's number is probably similar. I'm not sure how you would evaluate, but without further ado, John.
Well, okay, that's too much really, but yes. So where are we? So the title of this lecture is some kind of attempt to drum up enthusiasm for this book. It's the same as the title of the book, namely The Symmetries of Things. And what do I mean by things, you will ask? Well, I'm thinking of quite homely things, like, well, let's say chairs. Here's this a nice chair. Now this has a very simple kind of symmetry. Oh yes, what do I mean by symmetry? That's probably a good thing to say first. Well, I mean some kind of way of, let's say a geometrical congruence that puts the chair, or whatever object we're talking about, back in the same place that you started. Well, there are two for this chair. One of them is the identity, you just leave it where it was, and the other is to reflect in this vertical plane here. Okay, so that's the kind of symmetry that's most common. We all have an approximation to that symmetry, you know. We have not only a left arm, but a right arm, and so on, which is roughly the same as its mirror image. Not exactly, you'll notice. If you see yourself, you know, you most often see yourself looking into a mirror, so you see the reflected self, not the real self. And if you have occasion to see what your real self is like, you get a little bit of a shock, because it's not the picture you normally see. Okay, well, symmetry has long been of interest to all sorts of people. If you're building, for instance, a bridge, a really big, expensive bridge, then they usually have fourfold symmetry. There's a reflecting plane in one direction and a reflecting plane in the other, and if you sort of cut the bridge along those planes, you get 4 quarters, and each quarter is congruent to all the other quarters. And that saves money, if you want to save money anyway, because you only have to do a quarter of the design work, really, do a quarter of the calculations and so on. In solving mathematical problems, symmetry often enables you to save effort in some way, because you can say, well, without loss of generality, we discuss the left-hand side, roughly speaking, or whatever it is. So symmetry is a very practical subject. That's not really the reason I'm interested in it. It's a very beautiful subject. In general, my typical way of thinking of a highly symmetric object is to think of some kind of gem, which has many facets, but a beautiful sort of rose shape or something in there. Okay. In chemistry, in geology particularly, symmetry arises in the ways in which things crystallize. And this was noticed a long time ago. If you have alum crystals, you can tend to pick out pretty close to regular octahedra, nice shape. But then there's another way. When you think of crystal symmetry, when geologists or mathematicians think of crystal symmetry, they actually think not of the symmetry of the crystal very much. They used to think of the symmetry of the crystal as a physical object here. But you imagine this crystal continuing, you magnify it up, and then there's a regular repetition of the atoms involved and so on. And you imagine that continued forever to infinity, and then there's an infinite symmetry group, the symmetry group of all the translations and rotations and reflections that fix that crystal pattern. Historically, the finite symmetry groups were enumerated first, and then roughly in 1890, the possible groups of this infinite kind I just mentioned for crystals were enumerated. There are about 200 of them. They were enumerated by 3 teams. Fedorov, the great Russian, I say teams, 2 of the teams only contained 1 member. All 3 of the teams contained only 1 member. Well, never mind. Fedorov, the great Russian crystallographer, who turns out to have done it first in every way, but then his work didn't reach the West, so to speak, until later than the other people. Schoenflies, who was German, and whose notation is generally adopted nowadays, and a less well-known but equally interesting figure, Peter Barlow, an English crystallographer, and the author of a book of mathematical tables that was still in use when I was a kiddie, as well. They enumerated these things. They each made a few mistakes. It seems to be a rule that if you enumerate at least 100 things, or something like this, then you'll miss one out, or you'll put one in twice or something. They did it all at about the same time, 1890, and in a few years from then, they communicated with each other, and the inconsistencies were ironed out, and the situation has stayed the same ever since then. And it's a staple of physics, chemistry, crystallography, and so on. Okay. Now, the ways they did those things, there's a theorem that the type of symmetry group we're having always, this infinite kind, always has a lattice of translations called the Bravais lattice in the literature. And so the way they did it was take every possible shape of lattice and discuss what symmetries you could add to this. This lattice is invariant under a rotation of order 4, while that one is invariant under some other rotations or reflections, and so on. And that lasted for essentially 100 years, no, perhaps 80 or 90 years. And then the correct way of doing it was found. And it was found by two people, really, independently, Murray Macbeth, who was at the time at Birmingham University in England, and William Thurston, who was one of my colleagues in Princeton. Not at the time, you know. I later joined Princeton and met Thurston. And I remember very much, you know, one of the assertions made, the two-dimensional analog of this kind of assertion, is something you may know, that there are 17 symmetry types of repeating plane patterns. These are often called the wallpaper groups. I think that's almost criminal to call them the wallpaper groups, because it leads people to expect to find them on wallpaper. And you can't find them on wallpaper. You can find about 4 of them on wallpaper. But if you go to posh hotels, you can often find mosaics in the lobby or even in the bathroom. And these and you can find them outside too. And the tiled patterns, you know, of these mosaics will exhibit all 17 different types. So I prefer to call them the plane crystallographic groups. I'm sorry, that's rather technical. Or if I want to be non-technical, I talk about repeating patterns or something. Don't say wallpaper, please, because, you know, it turns the students on and then disappoints them. You know, you set as an exercise, try and find examples of these 17 groups, and they comb the streets of, say, Providence, and they don't find any, you know. Okay. But I mentioned that the initial way of doing it lasted for about 90 years, and then the correct way of doing it was found. Well, perhaps I shouldn't say correct, the best way of doing it. I mean, the old way was correct, it was just rather long-winded, and turns out to have been, you know, not a good way to approach the problem. And that is the way of discussing what geometrical operations are in the group, you know, which operations of rotation or translation or whatever fix your object. And Thurston was a topologist, he still is, and he did it a different way, which is to consider the quotient of the space that you're acting on by the group. And that's called an orbifold. And I think the etymology of orbifold is orbit hyphen manifold. But it's not quite a manifold. Well, let's try and find the symmetry group of this chair. Well, somebody once said, I believe, but if anybody can find the quotation I'm referring to, I'd love to see who it was that said this, that even quite ungainly pieces of furniture tend to become spherical if you wrap them in enough brown paper. This is one of those great things, and it's true, so to speak. So what I notice about this chair is that it's finite. Fine. That's a good thing. It's not a repeating pattern through all of space. Okay, fine. So we can think of wrapping it in brown paper. We'd better take it outside this room because it gets a bit crowded in here, and you know. we want a lot of brown paper. Well, actually, let's not use brown paper. Let's use Emperor's new paper. Emperor's new paper is so wonderful and filmy and everything that it's just completely transparent. You can't even see it's there, but it is there, you know. And so here, by magic, I've wrapped it in some Emperor's new paper, and okay, here we are. And let's make the sphere rather bigger. Let's call it the celestial sphere. That's a pretty good idea. So, where are we? Yes. I'll simplify the shape of the chair, if you don't mind, because I'm not a fantastically good artist. Okay. So, there's the chair. And now we take some Emperor's new paper. I suppose a celestial blue is the right colour. Yes, every symmetry of this finite sort of physical object fixes its centre of gravity. So I don't know quite where the centre of gravity is. Let's say there, you know. So now if it fixes the centre of gravity, it automatically fixes any sphere whose centre is the centre of gravity. So let's have this sphere. You know, I probably am not drawing it too well. It doesn't look terribly spherical. Okay, so here's the chair wrapped in the imperial celestial sphere. Right. And what's the reason why I wanted the celestial sphere? Well, the celestial sphere is a rather simple kind of space. I mean the surface of the sphere, otherwise I would have said the celestial ball. The celestial sphere is a two-dimensional manifold. Okay. And moreover, it has all sorts of homogeneity properties and so on. The chair is a rather ungainly object. Okay. Well, now I'm going to write in red something that is sort of highly relevant here. It is, if you had the mirror that reflects this chair into itself, it's where it would cut the chair. But it's rather simpler to say where it would cut the sphere. Well, I hope I'm not, you know, drawing that so badly that you can't see what I intend. It would cut the sphere in this circle, which apart from the fact that I've drawn it vertical, we might call an equator, and so on. Right, now what's the orbifold? Well, what I mean by the orbifold is this. Remember I suggested an etymology for the word orbifold. That etymology is orbit manifold. So the points of the orbifold are orbits of the group. Okay, well this group only has two elements. So here's a point on the surface of the sphere. Let's call it x. Here is a point, the point that x is reflected into by this symmetry. I'll call that, let me call it y for simplicity. And then x comma y is a point of the orbifold, the set consisting of x and y. But z here,
use this one as a better marker.
yeah, okay. Z happens to be in an orbit of size 1. Okay, fine. And now what we're going to do as mathematicians we can't necessarily do in real life, which is to identify x with y and z with itself, and you know, every point with its mirror image across this mirror. And then, whoops, if the way to do that, so to speak, let's remove the chair itself by magic, it's not there anymore, and then let's come along and sort of punch the sphere so that the right-hand half of it sort of goes inward and collapses onto the left-hand half. So, in a sense, the orbifold is now a hemisphere. Okay? Fine. Now Thurston's wonderful idea, which actually was had before him by Macbeth, and nobody outside a rather small coterie of mathematicians knew about Macbeth, was that, but Thurston, by the way, took this idea and made it his own. And if that sounds like a description of theft, well, that's actually an impression I want to convey slightly, but not too much. I don't sort of mean that he knew he was thieving it, but he really made it his own and found all sorts of things about orbifolds and their relation to symmetry and so on that Macbeth did not. Macbeth only did a rather special case. On the other hand, that special case includes all the ideas, so what, you know. Thurston's idea is that the topology of the orbifold actually determines the group. That's an astonishing thing because the group is a metrical object. You know, it's got symmetries, which the members of the group are geometrical congruents, which means they're distance-preserving things. And yet, what's topology? Topology is the study of those things that are invariant. You know, distance isn't invariant under topological transformations or continuous maps. But it's Thurston's amazing observation that geometrical groups are in fact determined by their orbifolds. And it's part of his revolutionary program for proving things in topology, the so-called metrization conjecture, which Thurston made, and which eventually has been used to solve the Poincaré conjecture by Pólya. But so it really says topological problems reduced to geometrical ones. I mean, certain topological problems, which is rather strange. Anyway, fine. Well, let me take another piece of furniture. This time, since it's got things on it, I don't propose to disturb it. There's this table here. Now this has a rectangular shape at the top of it. What's the easiest way for me to come across that one? Well, oh God. Let me try to do it. Is this the black that works? So again, I'll take the shape to be a slightly different shape to the particular example I was looking at. Whoops. A rectangular table. And now let's draw the celestial sphere around it. Oops. Well, this is a bit like the Emperor's New Clothes. You can't see them terribly well. But now there's a reflection. Let me draw where the reflection hits the table, so to speak. Now we get two reflection lines at right angles to each other. And whoops, on the sphere, oh my, I've gone outside the sphere. Yeah, must stay inside the celestial sphere, memo. Anyway, here it is. Okay, well, I'm not going to bother to draw it all. The orbifold consists of, it's rather like a piece of orange peel here. Do you all understand it? That is a right angle. If you cut an orange into quarters in this sort of obvious way, and then eat the orangey part, the good bit, and then the peel will look rather like this. Fine. Now, I think I want to start describing the notation. Perhaps I should say, when I first met Thurston, I said to him, something, I said to him, I have a rather nice notation for the 17 plane crystallographic groups. Let me show it to you. Thurston was always rather irritating if you wanted to show him anything. He said, no, let me show you my ideas first. And I said, well, what gives you the right to have first go? I said it first. I proposed all this discussion. He said, well, anyway, do it. So I said, okay, well, look, how about you taking 5 minutes, and then I take 10, and then you take 10, and then I take 10, and so on. Will you accept that? He said, yes, but I won't need more than 5 minutes. So he took his 5 minutes. And I'm not normally a modest person, but after Thurston's 5 minutes, I didn't bother to take my own 10 minutes or any time, because I realized his ideas were much better than mine. And that was, well, it was a surprise to me, but it shouldn't have been, because he's a very famous topologist, and he's made his life's work in this way. It was obvious that this was the right way to do things. And then I became a propagandist for Thurston. And I'm still acting as a propagandist for Thurston in this way. Okay. So what we've got to do is describe a notation, a way of naming these orbifolds. Now that's what I provided in the end. I said, I will find a beautiful notation which will make your ideas very clear. And I did exactly that. So let me say what the notation is. In this case, where I'm going to gradually introduce the various features. You look at the orbifold, and you'll notice things about it, and then I'll tell you the notation for each feature. It turns out there are only 4 features, only 4 types of feature, perhaps I should say. And once you've got them, you've done a lot. The notation for this orbifold, which you'll remember is a hemisphere, is star. So this is star. Star indicates a group of order 2. There are precisely 2 operations here. But what star really names is not the group operations, but the effect on the orbifold, the way in which they change it from being a sphere, which is the simplest sort of thing it could possibly be, to something more sort of complicated. And one of the things you can do to an orbifold, or to, let's say, to a manifold, is cut a hole in it. And star really means I've cut a hole in it. So this hemisphere can be regarded as what's left of a sphere when you've cut out a hemispherical hole, the other hemisphere. So star is the name. Well, we're only talking topology. Star is the name for a disk, because a hemisphere is a disk topologically. Okay. It has metrical information as well. It's not only a topological manifold, but it turns out that the topology is the most important thing. That's all you need, really, which is a remarkable discovery, because, as I say, what we're talking about are geometrical congruences which are defined to be the things that preserve distance. Okay, so that's star. Now this one up here, oh, by the way, usually well, let's say this one is star, because after all this is a disk, but remember that star really names the hole in the disk. And then 2, this is a red 2. And let me redraw the thing, emphasizing just the topology. There's a right angle there and a right angle there, which is the angle is actually pi over 2 up here and pi over 2 down here, and then there's a hole. This is the group I call star 2, 2. Okay. So that is the symmetry group of a rectangular table. Let's suppose instead that the table had been square. Now, if the table were square, I'll just sketch it very quickly down here. Then there's more symmetry, namely, as well as reflecting it in these two lines, and let me just sort of continue them around there to suggest the sphere without having to draw it. You understand me? But as well as those two lines, it's also symmetric under reflection in these lines. I'm sorry, I'm not controlling where the lines go exactly. Okay. And the orbifold is a rather thinner version of the thing I've described, which is this. And this angle is now pi over 4. And so the table is star 4, 4. Okay. Well, other things can happen. So far, these have really been kaleidoscopic groups. If I fix two mirrors facing each other at an angle of pi over 4, and I then put a random object in between the two mirrors, I will see something whose symmetry group is star 4, 4. There can be more complicated kaleidoscopes than that. So let me, where did the eraser go? Okay. A cube. Has really rather a lot of reflection. It's going to be hard for me to remember where I'm putting these. There's a line there. Okay, one of the coordinate planes of the cube. There's one here. There's one there. But then there's one that does this diagonal and goes all the way around and so on. There's one that does this. Well, I'm not going to bother to draw them all. I suppose I should, because I should be a bit more patriotic. This cube has a Union Jack on each face. Okay, but now the orbifold has angles, right? Now, what are they? Pi over 4 up here, that's that one. Pi over 2 here, and that's there. And then pi over 3 here. Now, don't get confused. I drew this network of lines on the surface of the cube. But it's really not on the surface of the cube, it's on the celestial sphere. And so the angle here is not 45 degrees, okay, because 6 of them make up a whole revolution. It's 60 degrees. It's not pi over 4, it's pi over 3. There's another way to think of this. We can ask, how many mirrors go through the point? And there are 4 mirrors going through this point in the face of the cube. Can you see it? There are 3 mirrors going through the vertex, and there are 2 mirrors going through a point on the edge. So this has kaleidoscopic points of orders 2, 3, and 4. And okay, and so let me draw it again and not be too worried about getting the angles right, because as long as I label this 4, 3, 2, and put a star there, remember only the topology is important really. So this is star 4, 3, 2 is the symmetry group of the cube. Okay. But now suppose that we didn't take all the symmetries of a cube, but only say the rotational symmetries. Well, oh God, it's gone again. No, it hasn't. If we take the rotational symmetries, a curious thing happens. The best way of indicating this, although it's, in view of fairly recent history, it's not too nice, is to draw a swastika on each face of the cube. Oh, sorry. It's a great pity that I sort of always feel a bit guilty when I do this, but I really shouldn't. I mean, the swastika is a nice geometrical pattern and was known in ancient India and so on. Okay, so now the object we're thinking of is this object, and it doesn't have any reflection symmetries at all. These are all, as it were, right-handed swastikas. Actually, there's another name. One tends to think of swastika as a German word, but it's not. They called it a Hakenkreuz, but it's really an Indian name. But this object has had many, many names over history, and one name for it, which I rather like, is the tetragamma, because it's made of 4 gammas. But anyway, what happens if you do that? Well, let me just take a piece of paper first. Oh, sorry. I'll take a piece of paper like this and just draw a swastika on it, and then wonder what that does to its orbifold. Can I steal a piece of paper from you? Oh, you've even drawn the swastika. Thanks. Well, is it okay if I rip this up? I was taught this trick. Okay, I was taught this trick by an elementary school teacher, how to tear paper up and get reasonably straight lines. But anyway, here it is. Now, how can I identify this up? What I've got to do is take this point here, say, and identify it with this point, and then also with this point, you know, and so on. Well, what I do is I tear my way to the center somehow. Doesn't very much matter how. And then I turn it into a sort of cone. I'm just fitting this X on top of that X. Okay. So this is what happens when your symmetry group contains a gyration. Now, a gyration is a rotation. Well, let's say a gyration point is a point of the figure through which there's a rotation that takes it to itself, but that point is not on any reflection line. Okay, not. You notice I emphasized I emphasize that word because experience teaches me that people forget that condition. So I get rather annoyed with them and it's more efficient to get annoyed with you before you make the mistake rather than after. You know, you learn quicker. Okay, that's called a cone point. And this is a cone point of order 4, and the angle is 2 pi over 4. Because before I did it, there was 2 pi's worth of space, a whole revolution of space around this point. And now there's only 2 pi divided by 4, 90 degrees. Okay, so this is the orbifold of the original square with the swastika on it under this rotation of order 4. It's rather harder to see it in more complicated cases, but there's something else I wanted to say about it. The concept of an orbifold can be made to carry some metrical information, and in particular the angles, the total amount of space around the point is quite important. This point is really only a quarter of a point, because a full manly sized point, you know, has 360 degrees around it, but after this identification it only had 90 degrees. So it's only a quarter of a point. That will be quite important later. So what's the orbifold of the cube under its symmetry groups? Well, it turns out that the only important thing really is what the singularities, cone points are singularities, are. And there's a singularity here. This is a 4-fold cone point. There's one here. That's a 3-fold cone point. And then there's one here. That's a 2-fold cone point. If you locally rotate the thing through 1/2 a revolution, or 1/3 of a revolution, or 1/4 of a revolution about these respective points, it comes back onto where it was. And a revolution, remember, is 2 pi. We work in terms of units of revolution. So this group is 4, 3, 2. And you notice I've changed colour. There's a colour convention in this notation. Red is involved with reflection. Blue, well, they're true motions, so to speak. Okay, that's this group. Well, now, it's a wonderful thing. Let us try to work out what the Euler characteristics of these various things are. Now, you possibly remember the definition of Euler characteristic, V minus E plus F. You draw a map on your object, and then you count V is the number of vertices, E is the number of edges, F is the number of faces, and V minus E plus F is an invariant of the topology. Now what we have here is an extension of the notion of Euler characteristic. So let's draw a map on this orbifold here, which has one face, which is this two-sided thing. Okay. And well, let me say something that's wrong. It's going to have 2 edges and 2 vertices. That's the wrong thing. But no, that's not true, because this edge is only half an edge. Euclid was wrong when he sort of defined as, you know, lines are things that have no thickness and so on. Lines have a thickness, let's say. We can, let me take this green here. Here's a line. Okay. And here are some vertices, the end of the line, and so on. And now, and the green thing is going to be part of my map on the surface. And now I'm going to start considering what that becomes in the orbifold. Well, you know, I'll make it a bit, I'll suppose that at the top here there were several edges coming in. What happens now is the mirror line goes along the edge of the map, and the edge was this quite thick green line. and it splits it into two. And then there's some other reflection line of the map, maybe. I don't quite know which map I'm talking about. This is only an example. And it goes, these red lines go through the vertices and split it into 6. You know, this vertex here is split into 6. So the part that comes out in the orbifold is only half an edge here, the right-hand half. And the part of this vertex that comes out in the orbifold is only 1/6 of a vertex, and so on. So now let's try and work out the Euler characteristic of this thing. Well, there's V in this case is 2/4. Okay, because we've only got 1/4 of a vertex in there and 1/4 of a vertex down here. And then E is 2/2, because I have a half of an edge there and half an edge there. And F, however, is 1. So the Euler characteristic, so this is of course another way of saying 2/4 is a half. 2/2 is 1 plus 1. So the characteristic is this thing, which is a half. The Euler characteristic of that orbifold is a half. This is appropriate because the Euler characteristic, the orbifold, is a sort of divided manifold. And so the Euler characteristic is performed by doing the corresponding divisions on the vertices, edges, and faces. Let's work out what the Euler characteristic, where did I draw it, of star 432 is. I don't seem to have got it anymore. I must have rubbed it out. Let's work it out again. So star 432, let me just remind you roughly what it looks like. Is a 4 and a 3 and a 2, and I put star there to indicate there was a hole. Well, what's here is only 1/8 of a vertex. Oh, sorry, I must write in a different colour. Remember, this was what came out of the vertex at the centre of a face of the cube, and it was on 8 triangles, so only 1/8 of it is around on in one triangle. This is 1/4, and this is 1/6. So V is 1/8 plus 1/4 plus 1/6, which is some number of 24ths. 3 24ths and 6 and 4 24ths. 3 and 10 is 13. So the number of vertices in this map is 13 24ths. Sorry, 13 24ths. What's the number of edges? Well, the number of edges is 3/2, because there's half an edge here, half an edge here, and half an edge here. We only have the inside halves of the edges. And the number of faces is 1. So the Euler characteristic is 13 minus 36 plus 24 24ths, which is 13 minus 12, which is 1/24. Okay, and that's 2 48ths. And I usually measure these things in monetary terms. Ever since I came to America, all money is green, and it's measured in dollars. What's the significance of that? Well, this is the way you work out from the orbifold symbol what the order of the group is, how many symmetries there are. Namely, look, what is the orbifold? The orbifold is 1/48 of the sphere. We cut the surface of the sphere into 48 triangles. Remember, 8 for each face of the cube. And there are 6 faces of a cube, that makes 48. So the orbifold is 1/48 of the sphere. It's not a sub-manifold, it's a quotient manifold, but still, you know, it counts as 1/48th of the sphere. What's the Euler characteristic of the sphere? You ought to know. V minus E plus F is 2. That's Euler's original theorem. So, so when I work out these Euler characteristics, if they come out to be fractions, I always renormalize them so that the numerator is $2, because I think of this in properly American terms as an amount of money. But there's another way of getting to it, which is this. You can work out for each feature of the orbifold what it does to the characteristic. And it turns out it's like paying for a menu. And I want you to think of it like this. Your mother, when you go out in the morning, gives you your daily allowance of $2. She says, now be good, don't spend too much and so on, you know, don't be profligate. And then you buy various things and you have some change, And let's discuss what happens if we buy, for instance, the symmetry group of a cube. Well, it turns out that here's what everything costs. Yeah, we've got it. This is the menu. Star costs, whoops, $1. I'll explain why later. A red number after a star, well, here it is, 2, costs half a dollar. 3 costs 2/3 of a dollar. 4 costs 3/4 of a dollar. And so on. You can guess what the general rule is. It costs $1 minus 1/10 of a dollar. That's what the red numbers cost. The red numbers are children. The blue numbers are adults. And have I got this right? No, I've got this wrong. Curses. Okay, well, I'll correct it. It was the blue numbers that cost those things. And the red numbers are the children, and they cost half as much, namely, namely, $1/4 of a dollar, 1/3 of a dollar, and 3/8 of a dollar, and so on. And in general, a blue N costs N minus 1 over N dollars, and a red N costs N minus 1 over 2N dollars. Okay. Let me try to explain why. I don't think I'll write anything about this explanation on the board, but I'll just say it, and I've got to keep the colours, the caps on the right colours. I'll say why these things cost what they do. Well, the first thing is, if you punch a hole in the manifold, the significant thing you do is remove one face. Okay. Well, no, that's not all you do, though. You also halve the edges and vertices around that face. But there are just as many edges around that face as vertices, so that doesn't do anything, because V and E are equal, and so V minus E cancels. So when you punch a hole in the thing, you reduce the Euler characteristic by 1, because it was a face. Okay, that's when you punch a hole. What happens when you introduce a corner? No, I won't make it a corner. I'll make it a cone point. Well, do you remember when I had this object? Before I made it a cone point, this was a man-sized point a full point. But after I made it a cone point of order 4, it was only a quarter of a point. So what have I done? I've subtracted 3/4 of a point. That's why a cone point of order 4, that's to say a blue 4, costs 3/4. Okay? And what happens, why does a red number cost what it does? Well, if before I introduced, let's say, this corner, there wasn't a corner there, and all the points along this edge were half points, because only half of the angle is there. After I've introduced it, I made this a quarter point, okay? Or in general, I made it 1/2 of a point if there were n mirrors meeting at it, and so that explains why the red digits cost half. They were originally half points, and they later became 2/n of a points, and that's exactly half of what the blue things did. So when we took the symmetry group of the cube in the form, which one was it? This group, I started off with $2. So let me try and explain. That's what my mother gave me when I set out in the morning. I'm now going to do the calculation. I think I'll do it in black rather than green. The cost of this is 3/4 plus 2/3 plus a half. That's written on the tariff over there. Okay. And so the change is 2 minus 3/4 plus 2/3 plus a half. And if you work it out, that turns out to be 2/48 of a dollar. My mother is rather irritating. She always says, there's a little homily, you know, let me see the change. And I hold out the change in my hand, and she says, you started off with $2, and you've come back with only 1/48 of that. She always says it in the form of what my original capital has been divided by. That's the number of symmetries down there of the cube. Well, I won't... yeah, when did I start? 4-ish, wasn't it? Yes?
The total amount?
Yeah, no, when did I mean, I should be stopping now. Say yes.
Take your time.
Well, well, I'll tell you roughly what happens. So take a finite symmetry group acting in three-dimensional space, fixing some piece of furniture, say, and therefore acting on the celestial sphere. If that symmetry group has order n, in other words, if there are n symmetries, then the Euler characteristic will be $2 divided by n. Okay, and you understand why, because the orbifold was the sphere whose Euler characteristic is $2 divided by n. Fine. And you'll notice that that number is positive. If you take $2 and divide it by a positive integer, you get a positive number. And so the Euler characteristic of a finite group of motions of three-dimensional space is a positive number. That's a wonderful thing. We can work it out by this recipe. Okay, there's a cost for each symbol, which is given on the tariff over there. And so whatever the ways of fitting symbols together that can be the notations for finite groups in three-dimensional space are ways of buying something at a menu with this, at a restaurant with this menu, that leave a positive amount of change. Okay, that's a truly wonderful thing. Now I'm going to tell a lie now, in the interests of simplicity. Well, I'll tell it a bit later. Actually, I won't tell you when I'm telling it. That's a good idea. Now, suppose you take an infinite symmetry group, in other words, a wallpaper pattern on the plane, and work out its orbifold. Well, what you get is, by a sort of limiting argument, $2 divided by infinity, which is 0. So the symbol for a wallpaper pattern is necessarily an item on the menu, a way of buying something at this restaurant here that costs exactly $2, so you get 0 change. Okay? It turns out that there are precisely 17 ways of doing that. If you go to that restaurant and want to spend exactly $2, you can buy 17 meals. Isn't that a wonderful theorem? That's the reason why there are 17 of these plain crystallographic groups. Okay, what happens if you only want to produce a finite group? Well, you've got to produce less than $2. You go home to mummy and have some change. And again, there's a correspondence between those things. What happens if you want to spend more than $2, you profligate little child? Well, then it turns out you're buying a group of symmetries of the hyperbolic plane. So you can get the enumerations of these 3 types of groups just by asking what symbols there are that cost the appropriate amounts. Okay, I've successfully told the lie. What was I going to say? This is the new way. This is the way people should have enumerated these groups. That's the message, really. I'm sure there's something else that I should have said.
Can I ask a question?
Yeah, okay.
Is this related to Gauss-Bonnet theorem?
Yes, it is. The Gauss-Bonnet theorem says that the integral, the integrated curvature over the manifold is 2 pi in the case of a sphere, but over the orbifold it would be 2 pi divided by n, where n is the number of symmetries. Or if the orbifold is obtained from a torus, that's a thing of characteristic 0, the integrated curvature would be 0. Yes, that's the, so to speak, the analytic aspect of this stuff. Very good question. I didn't pay you to ask that, did I?
Well, thank you, Professor. Any questions?
Yes.
Insights into why the common torques of this menu is 17.
Listen, it just happens that's what it is. I mean, it could have been another number, and then the theorem would have said the number of these plane crystallographic groups is that other number. Let me tell you what they are. I mean, it's quite easy.
Do you want to put this in your pocket?
No, I think I'll just go unencumbered. Or where is it now? Is it still attached to me in some funny ways? Okay. Okay. So let me name them. You see, if you have just blue numbers, it's really quite easy to work out what goes on. If there are 3 blue numbers, well, let me just tell you what the answers are first. 6, 3, 2. I'm doing the case of plane crystallographic groups. 4, 4, 2, 3, 3, 3, 2, 2, 2, 2. And then I'll add something which is if you, or well, maybe I won't do that. If you have just rotations in your group, then the sum of the reciprocals of these numbers has to, just 3 of them, has to be just 1. Because the sum of 1 minus the reciprocal, 1 minus a quarter plus 1 minus a half plus 1 minus, plus 1 minus a quarter plus 1 minus a half is 2. Okay, now whenever I have 2 equal blue numbers, oh no, I won't do that. I'll put star 632, star 442, star 332, star 222. Since a red number costs half of a blue number and a star costs $1, these also cost exactly $2. And now I can replace 2 equal copies of a red number, whoops, by a blue number, because a blue number costs twice as much as a red number. That's, one of the advantages, the only advantage of having had a stroke, is that I had to learn to write left-handed, and so now I can do either. Where are we? If I can remember which colour I wanted to write here. Oh, that's a 3 there. And this can be replaced by a blue 2, star 2, 2, or another. I can replace these 2 blue 2s by these 2 red 2s by a blue 2. So I've verified that all of these things cost exactly $2. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's the way it goes, basically. I mean, there are some other things that I didn't mention. For instance, you could have 2 stars that cost $2. But if a star gets to the end of a symbol, you can replace it by a cross. What a cross is a cross cap on the manifold. That's another way of changing the manifold. It changes the topology now. And then this star is at the end of the symbol. It's only followed by crosses. So these are a few more. Then I could have just left the orbifold be a torus, which is a sphere with a ring on it, and so on. Anyway, there are just 17 ways you can do it. I mean, there's no magic to this number 17. You know, there's a combinatorial problem being solved. It just happens to have 17 solutions. You can verify it if you like. Well, except that I didn't quite tell you all of the symbols. This circle, it's a torus. Oh my. 2, 2 cross. This star got to the end of the symbol, and when it gets to the end of the symbol, I'm sorry. I thought I was still some way off the end. When it gets to the end of the symbol, you can replace it by a cross. Let me discuss what happens. The orbifold, if you ignore the singularities on it, you just get a manifold. And we know the complete classification theorem for 2 manifolds. They're all obtainable from a sphere by adding handles, and that's what a circle gives for you. I seem to have rubbed out the circle I wrote. Or cross caps. And so the first thing to do is decide on the overall topology of the manifold. And then you can add singularities, which are to punch a hole, that's star, or to convert something into a cone point or a kaleidoscopic point. Those are the only features you can have by the classification of 2 manifolds, essentially. And now we have to see which of those 2 manifolds have a total cost of $2, which means there's no change. And then we've got one of the plane crystallographic groups. That was a rather hurried explanation and a rather incomplete one, but that's what you do. This is connected, incidentally, with Thurston's wonderful work on 3 manifolds. But there the information transfer is in the other direction. You know, how does this work? Well, we have had for a century now a complete classification of two manifolds. And essentially, this enumeration of groups is parasitic on that. Because you can completely enumerate two manifolds, you can completely enumerate two orbifolds, which are essentially the same thing as symmetry groups. But the real power of Thurston's ideas lay in the three-dimensional case, and there the information transfer was in the other direction. We don't have a complete enumeration of three manifolds. We still don't. But Thurston realized that maybe you could use these ideas to get information about three manifolds. And that was his metrization conjecture, which has now actually been proved. And the simplest thing you get in that direction is the thing now known as Pellman's theorem, or the Poincaré conjecture. But the next simplest thing, also handled by Perelman, was proving Thurston's conjecture about the nature of three manifolds. They are all cuttable into pieces, and each piece has a metrical structure, and then you glue the pieces together in certain ways. And there are seven or eight different types of piece, I forget which. And so in this case, we didn't have the classification of manifolds to start with, but we deduced something about it from the geometrical situation.
Any other questions?
Right, thanks again.